Alright, hello class. In this video we're going to jump right into where we left off in the last one and continue talking about double integrals. So we are going to be looking at examples where we have to reorient the way we think about a region, think about it in terms of, say, left or right versus bottom and top. And this is where things get really squirrely, okay? So definitely, if you haven't seen that first one, make sure you go back and watch it, because we're going to just go right in to the next example. Okay, now here is an example to show. I'm keeping the region still simple, but it's to show why we need to know how to orient in both directions. Okay, because the reasoning is, well, what we have here is just like we had before, that our inner integral is in terms of y, right? So that means we're talking bottom to top, which is how we usually like to talk about integrals of this type. However, there's a problem with this integral. E to the y squared, there's no integral rule for, right? This is actually impossible. Okay? Specifically, though, in this order. Okay? And that is the big thing, because if I could instead start with the x integral, oh, well, that would be wonderful, because with an x integral, this would just be a constant. Right, and I could actually integrate it, whereas when doing this with a y integral, this is a horrible thing in that variable. So we want to switch the order. Right? However, we can't just do this. We can't just say, oh, well, if I just want to switch the order, then I'll just switch the order. Okay? First of all, one, it does not work that way. Two, even if it did, since this is just a constant and we're integrating from 0 to 1, this would come out to just be the integral from x to 1 of e to the y squared dy, and we end up with the same problem, right? It didn't actually fix the problem. So remember, when we swap the order, this is what's not right. We can't have variables on the outer integral. They have to be on the inner integral. So instead, to swap the order, we have to completely change it so that I have x going from left to right and y going from C to D, right? This is what we have to do to get this reordered so that we can actually integrate. Okay, so let's take a look at how we would do that. Okay, so how we're going to start is, well, we need to start by seeing what R looks like. So we're going to graph R based on the information we have here. We know what the bottom is, we know what the top is, and we know what the x range is as well. Okay, so I'm going to clean this up a little bit and come back with a clean graph so we can start working on this. Okay, so when we go to figure out what the graph of R looks like, we do this in the same way. We have the bottom, the top, and we're going to work on it from here. Y equals x. That's the oops, wrong button there. That's just this line here, right? So here's y equals x. And then y equals 1, that's the horizontal line, say here. Okay? Now, since we're talking bottom to top, we need to know, well, what are we talking about? Are we talking about this region over here, this region over here, this triangle here, this region over here? Okay, and this is where we start looking at our x's, because our x's go from 0 to 1. Okay, so 0 to 1. Okay, so we're only living in here. So then it's a question of, all right, if we're living in here, is it, say, this lower triangle or this upper triangle? Okay, and that's where the bottom to top comes in, because we're told that y equals x is the bottom. Right, so that means when we go from bottom upwards to top, we're going to hit this guy first and then hit y equals 1. So here's our bottom, here's our top. Okay, and so what we're talking about is, I like to draw, say, vertical lines, right? And what we're talking about is this green triangle here. Okay, so this is our R. Now, this was thinking about it in terms of bottom to top, right? Now I want to reorient left to right, right? Because we want to swap this order of integration. So I need to now start thinking about it left to right instead. Okay, so I'm going to clean this up a little bit and then start thinking about it in terms of left to right. Okay, so now if I start going left to right, and for this orientation I always draw, well, just draw lines left to right. The first piece I'm going to hit is this vertical line, right? And then I move through and then I hit this line. Well, that's going to make this guy our right side and this guy our left side. Okay, so our left side is this vertical line. Well, that vertical line is x equals 0. Okay, no problem, that aligns with here, but our right side is this y equals x line. However, when we put it in our integral, it's going to be the x equals y. Because remember, when we orient left to right, it's always x equals left to x equals right. Okay, so when we set up this integral now, right, in terms of x on the inside, okay, so now I just rewrote the integral here. Now my inner integral is going to go from x equals 0, right, that's what this vertical line is, to x equals y. So the left to right. Okay, the inside function doesn't change, except now it's going to be dx, and my y's, well, now we need to establish how far our y's go. So our y's, if we think about, well, we can't have any negative y's, we can't have any y's greater than 1, so our y's are stuck between 0 and 1. Okay, so y goes from 0 to 1. So notice, it's not even a matter of just swapping these, like changing the variables around. Okay, it swaps. The outer interval looks the same, but the inner one, not only did the line here swap from the top limit, right, swap up to the top limit, it swapped around. Okay, and so now that we have it set up, well, it just kind of follows. And here's where quick U substitution is really going to be helpful. And I'm sure I've mentioned before, but I have a video in my Calculus 2 playlist that details quick U substitution in a lot more depth than I can get into here. But yeah, from here, since it's just an x integral on the inside, this is just a constant. And whenever we integrate a constant, It's really just, it's that constant times the difference of the limits. Okay, so we're going to get now the integral from 0 to 1 e to the y squared y dy. Right, and if we simplify this, right, we'll have y e to the y squared dy, and this is where the quick U substitution will come in, because we'll leave the y here, the integral of e to the stuff as itself, divided by the derivative of the stuff. And provided the y's or the x's or whatever's left over actually cancels away, we're good. Okay, and now we can plug and chug to get e to the 1 squared over 2 minus e to the 0 squared, which is 1. So we get e halves minus 1 half. Okay. All right, and there we go. This is why we need to be able to orient in either direction. All right, so the tricky thing about this really is the setup. Okay, so what I want to look at is, for this particular example, let's just change the order of integration for this particular problem. Okay, so say we have the integral from 0 to 8 and the cubed root of y to 2 of f of xy dx dy. Okay, now the first thing to identify when we want to do this is, well, what's our starting order and how is it oriented? Well, we're starting with x on the inside, right? So that's going to be an x equals this thing to an x equals this thing. So if x is on the inside, that's oriented from left to right. Okay, so that's going to help us establish what our region looks like. So if we just want to change the order, this is our first thing to set up. All right, the next thing to set up is, well, we need to graph these, right? We need to figure out what these graphs look like. So x equals 2, that is this vertical line here, let's say. Okay, and then this x equals cubed root of y. Well, you know, that's one of those things I'm not super great at just knowing what it looks like off the top of my head. But if x is equal to the cubed root of y, and I cube both sides, that gives me that y is equal to x cubed. Now I do know what that looks like. Okay, and to make this look a little better, I might need to shrink this down a little bit. Hang on. Okay, so from here, the cubed root looks something like this, and this is definitely not drawn to scale. But yeah, it looks something like this. So we've got this going on. Okay, so I've got the vertical line, I've got the y equals x cubed, and now here's how I also go about isolating it. Then I start looking at the x's. So x is, whoops, sorry, not x's, the y's. Sorry about that. Next I look at the y's, and y equals 0, that is this horizontal line. Okay, and then y equals 8 is another horizontal line, and it turns out that when x is equal to 2, right, here is x equals 2. When we plug x equals 2 into here, we get out 8. Okay, so here's that horizontal line. Okay. Now, we have quite a few options, right, for what this thing could look like. And here's where we start doing our left to right idea. Okay, if we go from left to right, we're told that the left side of our region is this curve here. So this needs to be the left side, right? So here needs to be the left, and 2 needs to be the right. Okay, so we can't have this area up here because it would be swapped. And we're past 0 and 8 in the y. Okay, and we can't go down here because we're past 0. So left to right, it looks like we have this funky little region here. Okay, it looks kind of like a triangle, but actually it's this little guy here. Okay, so now that's how we oriented it left to right. To swap, we have to do bottom to top. All right, so now that I just redrew the graph over here, if we want to orient bottom to top, the first thing we're going to hit for our bottom is this base here. Right, so y equals 0 is going to be our bottom, and our top is this y equals x cubed. Okay, so if I get started over here, I'm going to leave the outer integral alone to start with, but bottom to top, our bottom is y equals 0, our top is y equals x cubed. All right, then that makes a y integral on the inside. The integrand doesn't change. And now I just need to figure out what x is going between. Well, x, well, we know it stops here at 2 and it starts here at 0. So x is going from 0 to 2. And there we go. We've swapped the order of integration. All right. Let's look at another example here. Let's find the volume of the solid bounded by the surface f of xy equals x over the square root of y over r, which is the region bounded by the curves x equals 1 plus y squared and x equals 9 minus x squared. All right, so this is an example where we're going to want to put x on the inside, mainly because we already have the curves in terms of x equals something. So this makes me want to orient left to right. All right, so I usually think this is a good practice to graph these guys. And if you're curious about how you should go about graphing them, and I'm sorry, I totally spaced on that. That's x equals 9 minus y squared. Okay. So x equals y squared plus 1, or 1 plus y squared. So notice this side is always going to be greater than or equal to 1. So it's essentially going to be a sideways parabola opening this way, right? And the reason I know that, if you're unsure, just move the 1 over and take the plus or minus square root, right? So plus or minus the square root of x minus 1, well, x minus 1 shifts it over to 1. Okay, so there is y, whoops, let me write it this way, x equals 1 plus y squared. Okay, now 9 minus y squared, that's going to be a sideways parabola opening the other way. Okay, so then it's a question of, well, what region is it that we're talking about? And remember, if we're talking left to right, and we're talking about bounded, it's going to be this region here. Because we're not really told anything else about it except this. Now we don't have to swap the order here, at least I hope not. And the reason we want to leave it left to right, right, that's part of the reason about this example, is if we didn't, if we wanted to orient it bottom to top, notice that if we did that, first of all, in y we would have two integrals to deal with because the bottom and the top change halfway through. Right? So typically what we'll want to do is just leave it in the form it's given to us in. All right, so that's not too bad. So when we go to set up our integral, I'll leave the outside ones alone for just a second. What we're going to do is left to right. So our left is this guy here. That's the 1 plus y squared, and then the right is this guy here, the x equals 9 minus y squared. Okay, now how we find the y limits is, well, we want to see where these guys intersect. Okay, so we're going to set them equal to one another and solve. So we're going to set 1 plus y squared equal to 9 minus y squared and solve. Okay, so I'll move this y squared over. So I'll get 2y squared on this side is equal to 8. Okay, so y squared is equal to 4. So y is equal to plus or minus 2. All right, so we're going to go from -2 to +2. All right, and there we go. We've set up our integral. Once we put this in here, x over the square root of y, and I'm actually going to write this as y to the -1/2, and it will be dx dy. All right. And I just realized something. My note, I copied this down from my notes wrong. I am very sorry about that. Thankfully, we haven't used it very much yet. This should be y over the square root of x. Sorry about that. Hopefully that doesn't mess things up too bad for you guys. Okay. Now, we're just going to integrate this. Okay, so I'll leave the outside guy alone, and now I'll just integrate this in terms of x. And so we're going to get x to the 1/2 divided by 1/2, which ends up being multiplying by 2. And we are going to evaluate this from x equals 1 plus y squared to x equals 9 minus y squared. Right, and we'll have the dy on the outside. Okay, now we'll plug and chug with our fundamental theorem of calculus, and we'll get -2 to 2y. And let me take that 2 out here, and then inside we'll get, it's x to the 1/2, so it will be 9 minus y squared to the 1/2 minus 1 plus y squared to the 1/2. All right, so now we'll get -2 to 2 of 2y times 9 minus y squared to the 1/2 minus 2y times 1 plus y squared to the 1/2 dy. And now we can integrate with respect to y. So here is, thankfully, once again, where we can use quick U substitution. Okay, it's going to really come in handy here because I have the derivative of the inside sitting on the outside, essentially. Right, so for quick U substitution, I'll leave the 2y alone. Then it's going to be 9 minus y squared to the 3/2, right, times 2/3. Then I just need to divide by the derivative of the inside, which will be negative 2y. Okay, and the 2y's cancel. And then here, it's the same idea. Minus 2y times 1 plus y squared to the 3/2. Put the 2/3 out here. Divide by the derivative of the inside, which in this case will be simply the 2y. And they cancel. We're going to be evaluating these from negative 2 to 2. Okay, so we're going to get 2/3 times 9 minus y squared to the 3/2 minus 2/3 1 plus y squared to the 3/2, and we will evaluate this from negative 2 to 2. All right, so we'll get 2/3 times 5 to the 3/3 minus 2/3 times, well, it'll also be 5 to the 3/2. I think I said 3/3, 3/2. Okay, and that's actually kind of interesting because that will cancel. Then we'll plug in the negative 2, but that's actually not going to change anything because we're just squaring this number anyway. So we should get 0 minus 0, which is 0, and we get 0. Well, that might seem like a strange result. So let's see what's happening here. All right, to get an idea of what's going on here, here is the graph of y over the square root of x. Okay, and the region that we're integrating over is this one here, right? There's our region R on the xy plane. And if we trace that out along our region here, along the surface, okay, so let me get rid of that. All right, then if I just show the surface that we're integrating over, you'll see that the same amount of it lives above the xy plane as it does below the xy plane. Okay, so let's show the plane here. Yeah, there's the xy plane. And so we can see that it's actually symmetric, right, across the z-axis. We can... Okay, so what's happening is we got an integral of 0 because, well, the volume on this side, right, cancels out the volume on this side. So just like with normal single integration, this is net volume. So this shape lives exactly in the negative z's as much as it does in the positive z's, over this region at least. Therefore, that is why we get out to 0 at the end. Okay, so to end this particular lesson, I want to talk about rectangular regions because this is actually the simplest form of region we can talk about. And it's the book likes to start with this, but I prefer to start with the tougher version of it and then show that this is a very special case of what we already know how to do. Okay, so a rectangular region is basically just a region where we have all the points x, y, and this is sometimes how the limits are given to you, where x is simply between a and b, and y is between c and d. Okay, it's when our limits are all constants. So all constant limits. Okay, and the reason it works this way is because, well, if let's say x equals a is here, and x equals b is here, and then let's say y equals c is here, and y equals d is here, between all of those values, we have this region here, which turns out to be a rectangle. Okay, and the beauty of a rectangular region is, well, if I talk about this in terms of bottom to top, it's y going from C to y going to D. And if I talk about it in terms of left to right, well, the left is still x equals A to x equals B. So this is the only case where you can swap integrals without a lot of work. Okay, and this is such a big deal, it actually gets its own theorem, which is Fubini's theorem. Okay, and what Fubini's theorem says is that if f is continuous, so let f be continuous on the rectangular region R, right, defined in the same way we did before, then the double integral of f of xy dA over R can either be written as the integral from C to D and A to B of f of xy dx dy, or in the other order with the y first and the x second. This is the only case where this works, and this is just a special case of what we've been doing. Right? It's just easier, okay? When you have all constant limits, it's so easy. You can just flip things around willy-nilly however you want, but this is the only case where that works. Okay, so I'm going to do a couple more examples here, detailing this or showing this, and that will be that for this particular section. Okay, so let's take a look at this integral here. We want to find the double integral over R of y e to the xy dA, where R is this rectangular region here, where x is between 0 and 1, and y is between 0 and natural log 5. This is a rectangular region because these are constant limits. Okay, so constant limits implies rectangular region. Okay, that means we can set this up in any order we want. Right, so I could say that this is going to be 0 to 1, and then 0 to ln 5, y e to the xy, dy dx, or we could set it up as 0 to the natural log of 5, 0 to 1, y e to the xy, dx dy. So we can do the x's first, or we could do the y's first. Now, in this particular case, there's an order that actually will be easier. Oh, well, how do I know that? Well, if I try to integrate this first with respect to y, I have a y on the outside and a y on the inside. Doing this and treating the x like a constant, this is going to be integration by parts. Well, that's actually kind of gross. Whereas here, it won't be, because when we integrate with respect to x, it's just an x integral. All the y's are constants. All right, so this way is definitely going to be the easier way to go about it. I'll show both just to, show you that you get the same thing out. But yeah, if we can avoid by parts, we're going to. It's actually ironic because in Calculus 2, you learn all of these really nasty techniques. And then in Calculus 3, you do everything you can in your power to avoid them. But there are cases where you can't, so it's still good to know them. So anyway, we'll start with this order, right? So if we integrate e to the stuff, okay, let me just write this. It will be itself, so I'm going to leave the y there, that's just a constant. It's e to the xy, we need to divide by the derivative of the stuff. So I'm actually going to write this like this. I want to divide by the partial derivative of xy. Okay, and then we will plug in the 0 and 1 into x. All right, so we'll have the integral from 0 to natural log of 5, y, e to the xy, and the partial derivative with respect to x of xy is y. Okay, and now we're going to plug in x equals 0 and x equals 1. All right, so we get now the integral from 0 to natural log of 5 of plugging 1 into x, we'll get e to the y minus e to the 0, which will simply be 1 dy. Right? And now it's just a Cal 1 problem. The integral of e to the y minus 1 is simply e to the y minus y, and we'll evaluate this from 0 to natural log of 5. Right, so I have e to the natural log of 5 minus natural log of 5 minus, and I should remind ourselves of what we're doing here, minus e to the 0, which is 1 minus 0. So I always at least try to tell myself what I'm doing here, because plugging in the 0 doesn't always give us a 0, especially if we have an e or like a cosine. Okay, now e to the natural log of 5, this is actually equal to 5. Okay, so we have 5 minus ln 5 minus 1, so we have 4 minus the natural log of 5. Okay, now I do want to show we can do it this way. Okay, we can use integration by parts, especially if we do our quick integration by parts, where we have the derivative side and the integral side. Okay, so for the derivative side, I will choose the y. Remember, we're doing this in terms of y. And the integral side, e to the xy, which again we're doing in terms of y. So for the derivative side, it'll go 1, 0, perfect. And then for the integral side, and this is where it gets a little funky, here remember x is the constant. So when we integrate with respect to y, we're going to be dividing by that constant. Right? So it'll be 1 over x, e to the xy, then 1 over x squared, e to the xy. Okay? And so now we're going to do our plus and our minus. If you've not seen this before, once again, I have a video in my Calculus 2 lecture series that shows this table method. All right, so when we integrate this, we'll have the integral from 0 to 1, and now this is y over x, e to the xy, minus y, oh, not y, sorry, minus 1 over x squared, e to the xy. Then we're going to evaluate this from 0 to natural log of 5. We still have the dx on the outside. All right, now this is going into our y. And hopefully now you can see, like, you know, how this can get mixed up if we're not careful what we're plugging things into. Okay, we're plugging these into the y's. Now, when we plug this in, when we plug in natural log of 5, I'll get natural log of 5 over x, e to the natural log of, or let me write it like this, e to the x natural log of 5, okay, minus 1 over x squared, e to the x natural log of 5. So that's just plugging in the natural log of 5. Now when we plug in the 0, thankfully the e stuff will go away, and this whole term will go away. So we'll get 0, then minus 1 over x squared dx. Okay, so then we'll have the integral from 0 to 1 of the natural log of 5 over x times e to the x times ln 5 minus 1 over x squared e to the x ln 5, then plus 1 over x squared dx. Now, hopefully you can see at this point why we don't want to go in this direction. Okay, I'm not saying it's impossible, but we've now hit a point where, yeah, I don't want to do this anymore. Okay, so order matters. All right, that hopefully is the takeaway here, that order matters. All right, for a similar example here, if I have the integral from 0 to 1 and 0 to pi over 2 of x cosine of xy dx dy, this order is going to require integration by parts. However, if I swap the order, it won't. And since this is a rectangular region, swapping the order is just as simple as, well, swapping the integrals. Okay, that's simple. So, but again, keep in mind, this is only true for rectangular regions. Okay, so now we'll just integrate, right? We have the integral from 0 to pi over 2, and now it will be the integral of cosine, which will be sine of xy. Then we're going to divide by the derivative of the inside, and remember, we're differentiating with respect to y. So I'm going to write the partial derivative with respect to y of xy this time. Okay. Just to keep things clear for myself, so I have x sine of xy all over the partial derivative of xy with respect to y is x. And there we go, the x's cancel. And we're going to evaluate this from 0 to 1 and then take the integral with respect to x. Okay, so plugging in the 1, we will get, and keep in mind, what are we plugging into? In this case, the y. Okay, so we'll have sine of x when we plug in the 1 minus 0 when we plug in y equals 0. Okay, now we just need to integrate this. The integral of sine is negative cosine, and we're just going to evaluate this from 0 to pi over 2. All right, so it'll be negative cosine pi over 2 minus a negative cosine of 0, and this is another case where we can't just make the 0 1 0 because that's the pi over 2 that's 0. Okay, so it's negative negative cosine 0, so we get 1. Okay, so I think that's definitely enough for this particular lesson. In the next one, we're going to start looking at how U substitution can get even more complicated when you have two variables rolling around. Okay, so I'll catch you all on that one. Cheers!